Hey everybody, Mr. Fortin back here. You got yourself your second problem for class today on Tuesday, and it has to do with closed sets. More about number sets, and you're working on this, and you're like, okay, it supposedly came up before. I forgot all about lesson 3.2.3 when this came up here. What the heck? Anyways, we're doing it now, and the reason why we're doing this today is because it's kind of interesting to think about. Numbers exist for a reason, and sometimes we need different types of numbers. That's why there are all these different things we want you to learn about, like integers, whole numbers, rational numbers, irrational numbers, imaginary numbers. Anyways, numbers are useful for a whole bunch of different applications, and that's why different types of numbers exist. That's why you're kind of thinking about it. Okay. So, anyways, I know that these problems are a lot of reading, a lot to think about, maybe overwhelming, I'd say. But just keep in mind, I actually haven't assigned these problems in a few years. Probably been about 2 or 3 years. Okay. The reason why I'm assigning it to you today, okay, well, is because I wanted you to do problem 391. Oops, I have the wrong number on here. We're doing problem 392 now. 391 was your big practice problem today. You should feel pretty confident, I'm hoping, after watching the video for 391. Anyways, this lesson here, we're just moving very, very slowly, right? While I'm out, we're moving slowly. So I figured, hey, as we move slowly, why don't we also think about closed sets as we're thinking about solving equations and exponents and general rectangle. Anyways, closed sets, the problems are there, so let's think about them. Let's see if we can get them, okay? I have right here from the glossary, because I'm guessing if you started this problem, you're watching this video, more on closed sets, you might be like, I just read this. I have no recollection of this. What does this mean here? Lesson 3.2.3, you're told that whole numbers are said to be a closed set under addition, but not under subtraction. Well, we'll talk about that in a second. Then you discover that integers and polynomials are a closed set under both addition and subtraction. Oh, okay. What does that mean? I don't know. With your team, explore closure under multiplication as follows. Okay, so you're doing closure under multiplication, okay, for particular types of number sets, types of numbers, okay? This is it's really wordy, but I think you'll get it up. Oh, I got the answers here. I didn't mean to have the answers in this one. Sorry, let me white out the answers, and then we can talk about them a little bit later. Shoop. And I don't have the answers to the next part here. You might be worth looking at the glossary before getting started this problem. So here, I got this here. This is from the glossary, right? Glossary is in the back of the book. Okay, where did I get this from the glossary? I got it from over here. Oops, glossary over here. So page 676. How about that? Page 676, we got closed sets here. Glossary page 676? I don't know. It's in the back of the book here. Closed sets. A set of numbers is said to be closed under an operation if the result of applying the operation to any two numbers in the set produces a number in that set. For example, here, this is good. They're giving you an example. For an example, whole numbers are a closed set under addition. Okay? Because if you add any two whole numbers, the result's always a whole number. Okay? So to do these are these sets closed? You need to know kind of what some of these vocabulary words mean here. So for instance, whole numbers. Whole numbers are numbers like 2, 7, 16, 37, 512, 7,213, right? They're numbers that you don't see a decimal point because a decimal point is not necessary, right? It's a whole, right? It's not negative. You can't -2, -7, -16, -37. That's not a whole number. That would be a part of the set of integers. So anyways, these are whole numbers right here. And whole numbers are always positive, or they could be zero. Zero is a whole number. We got a whole bunch of nothing if we have zero here, okay? The idea with this is we take any whole numbers and we add any whole numbers together, we get a whole number as an answer. 9 is a whole number. Okay, I take 7, I add 16 to it. What do I get? I get 23. 23, is it a whole number? Yes, it's in that set. It's in the set. Our answers here are in the set that we are testing under addition. Do we need to invent new numbers, a new type of numbers? No, we don't. We can just stick with whole numbers. If we're just adding whole numbers together, we always get a whole number answer. I can take 37, I can add this 7 to it, gives me 44. Okay, so whole numbers are closed under addition, meaning that I take any two whole numbers, I add them together. What is my answer? It's always going to be a whole number. Okay, we don't need to say anything else about it. We don't need to say, well, whole numbers aren't good enough, right, to describe my answers here. Okay, whole numbers are also closed under subtraction. Okay, under subtraction here, because think about it. 2 minus, actually no, whole numbers not closed under subtraction. 2 minus 7 is -5. What's the problem with that? -5 is not a whole number. Okay, to be a whole number, you need to be like something like 0, 1, 2, 3. You got to be positive and you need to be whole. Okay. So, anyways, and they also say that here in the glossary here, whole numbers are not closed under division. Okay. If you divide any two whole numbers together, you don't necessarily get a whole number. Okay. Check it out here. 2 divided by 7. What does that equal? Well, I can try my trusty calculator right here because on top of my head, I don't really get that here. 2 divided by 7. Boom. Is that a whole number? No, that's something different, right? We need a different type of number to describe this. We need a decimal, okay? Or we need a rational. This is what we call a rational number because it's written using division, right? 2 divided by 7, 2, 8. So anyways, they just kind of want you to know that different types of numbers are necessary for different things, okay? So whole numbers are not closed, okay? Not closed under division, okay? Whole numbers are not closed under division. Why? If you divide any two whole numbers together, you do not always get a whole number, okay? The only way you're going to divide two whole numbers together and get a whole number is what? If the two whole numbers are the same, right? 7 divided by 7 equals 1. 1's also a whole number. So don't let this example confuse you because the set of whole numbers is not closed under division, meaning if I divide two whole numbers together, it doesn't always give me a whole number answer, okay? We need to go outside of our set, but this is outside, right? This is outside the set of whole numbers. So we could say that whole numbers are an open set under division. It's going to open us up to different types of numbers if we get our answers. Okay, kind of makes sense. Should we try it? I think we should try it here. Okay. Well, we discovered this previously. I don't know if I have to go over this here. Then you discover that integers and polynomials are closed set under both addition and subtraction. Cool, we did that. With your team, explore closure under multiplication as follows. Okay, so let's just get into it down here. Investigate with your team if the integers are a closed set under multiplication. Give examples of your conclusion. If you find that integers are closed under multiplication, can you explain how you know all integers are closed under multiplication? Let's check this one out here. Okay, let's try some integers. Okay, so this reminds us about what integers are. Integers are, I go back to your glossary actually. Go to your glossary if you're not sure what some of this stuff is here. Always be going to the back of the book. Check it out here. All right, two things that I don't see a lot of you guys doing is using your calculators to make your life easier to calculate answers, and then also look in the back of the book just to remind yourselves of what things are. HI, let's see, I'll get up to I, what an integer is. Okay, an integer. Who's got me? There we go. The set of numbers like this, how they define it like this. What jumps out to you about this? The integer is the set of numbers, ... -3, skip to -2, skip to -1, skip to 0, 1, 2, 3. So look, these are whole numbers here, 0, 1, 2, and 3. Are these whole numbers? No, they're not. Whole numbers need to be positive, okay? So what integers are the set of whole numbers, 0, 1, 2, and 3, and their opposites, okay? And their opposites. That's what they are. So let's first remind ourselves what the set, when you see this word integer, you mean -3, -2, -1. That's what should be jumping to mind is the negative versions or the opposites of whole numbers. So -4, -3, -2. So we're skipping. We're not including decimals here because decimals would be non-whole numbers here. So these are the opposites of whole numbers, -2, -1, 0, and the actual whole numbers themselves, 4, 5, and so on and so forth, okay? That's the set of integers, okay? That's the set of integers here. So the question is the set of integers a closed set under multiplication, okay? Let's test it. You got to test it to see if you can get it. So that means I'm going to take any two integers. Let's do it. I'm going to take this one and this one. -2 times by +3. Okay, test it under multiplication. What do I get? I get -6. Is this part of the set of integers? Is -6 an integer? Yeah, it is, right? -5, -3, right? It's an opposite of a whole number. So that's an integer right here, okay? 1 times by, 5. Okay, so we tested under multiplication. Is it still seeming like it's closed under multiplication? Do the set of integers, are they going to collect all of our answers here as we multiply things? Well, that's an integer, sure. Okay, let's test a few more. Let's test two negatives here. What about -4 times by -3? Okay, gives me +12. Is 12 an integer? Well, it's a whole number. Okay, whole numbers are also integers, right? Whole numbers, the integers are simply whole numbers and their opposite. So it's sort of broader, it's wider than what a whole number is here. So that's an integer. So we can say yes. Okay, yes, the set of integers is closed under multiplication. We're not open to non-integer answers if we multiply two integers together. We're always going to get an integer answer. We're going to get something from that set. If we multiply two numbers that are in that set, we get something from that set. So that's why we say it's a closed set under multiplication, okay? So yes, the set of integers is closed under multiplication. You can kind of justify it. I think if I look at the answer key and justify it this way here, it says, can you explain how you know all integers are closed under multiplication? What have you done with integers before, right? Think about that. What's the thing we sort of deduced or inferred before about integers in a previous lesson? We already knew what? Okay, we already knew that integers are closed under what? What did we do previously here? Previous lesson, 3.2.3, we got whole numbers, or actually integers are closed set under both addition and subtraction. Ooh, okay? We already knew that integers are closed under addition, so why would that help us prove that integers are also have to be closed under multiplication? Okay, we already knew that integers, we did that in a previous lesson, closed under addition. Well, okay, and since multiplication, where am I going with this? Multiplication, oops, how does it connect to addition? How does multiplication connect to addition? Yes, multiplication is repeated addition. Okay? Because multiplication is repeated addition. So if we're closed under addition, we're going to have to be. What would follow from that is we'd be closed under multiplication. Okay? Therefore, it must be closed under multiplication also. Messy handwriting. That's why you're listening here, okay? So anyways, I'll reread this thing here. Yes, the set of integers is closed under multiplication. We already knew that integers are closed under addition, okay? It reminded us of this at the beginning of the problem here. And since multiplication is repeated addition, right? Therefore, multiplication also must be closed because it's simply extending what we knew about the addition being closed. And addition and multiplication, they're pretty much the same thing, just multiplication is just the repeated addition, okay? Let's move on here. Are one variable polynomials closed under multiplication? Well, by that same logic, yes, they have to be, right? Yes, they have to be here. Hey, right? We already discovered that integers and polynomials are closed set under both addition and subtraction. Polynomials, if they're closed under addition, well, what's multiplication? That's repeat addition, so they're also going to be closed under multiplication, okay? As a starting point, you may want to think about some of the products below here. Let's just take a look here to verify this. This is a polynomial, okay, because, well, this is a polynomial here, because I have polynomial. What polynomial stands for, poly, the word poly, I think it's the Latin, right? Poly's Latin. Poly means many, okay? Nomial, the word nomial sounds like number, but poly means many. Nomial means terms, okay? So here I got two terms. I got two terms, an x plus a 2. This is a binomial. This is a polynomial right here. Two terms, right? Many terms. These are two terms right here. So I got two binomials. So I got a polynomial multiplying to another polynomial. What's my answer going to be? Is it going to be a polynomial as well? Well, I think we know it is here. Set up our generic rectangle. Let's see if our answer is also a polynomial here. X plus 2 times by 3x plus 4. Okay, I got 3x squared. I got 6x. I got 4x. Okay, I got 8. And my answer here, 3x squared plus 10x plus 8. Is that a polynomial? Yeah, right? I got three terms here. Remember, terms are separated by pluses or minuses here. What I should have done on this lesson was to have that math notes box, which tells you about polynomials, which I asked you to read, but hey, not that big a deal if we don't really nail polynomials this year. Hopefully you do fine here. Okay, is this a polynomial? Yes, it is, okay? What if I do this? If I do my distributive property here, okay? If I multiply that polynomial, right? This is a monomial, right? Just one term right here, okay? 9x times by the quantity 6 minus x squared. Well, I can just distribute that, right? 9 times 6. I always mess up 9 times 6, don't I? What is that? This is terrible. What is 9 times 6? Well, that would be 54, right? Yeah, 54. 54x. Okay, and 9x minus times by minus x squared. Well, x times by x squared is x cubed. Okay, I get the negative there. That's 9 minus 9x cubed. Okay, is that a polynomial? Well, sure it is. Sure as heck is. This is a binomial. 54x, that's a term. Negative 9x squared, cubed, that's another term. Terms are separated by pluses or minuses. That's a polynomial. Is this going to be a polynomial if we multiply the whole thing? Yes, it is, okay? I might as well practice it. 1, 2, 3. Okay, what's my height here? 3x squared plus 3. What's my width? I'm breaking up all my terms because I need to multiply all my terms together. But if we multiplied it all together, we would see that this is indeed going to get a polynomial sum as our answer here. Okay, so this is 3x cubed. The 3 times by x is 3x. If you're on a test, you're going much more slowly than this because it's easy to make mistakes. I've made mistakes on answer keys so far. And let's get our polynomial answer. 9x to the fourth. Combine like terms. Well, let's do the cubes part first. Plus 3x cubed. This is what I'm getting from my answer. I'm not going to check it just for the sake of time. Plus 12x squared. Okay, because I combine like terms here because these are my x squared terms. X squared pieces can go with other x squared pieces. X cubed pieces can't go with those if you're adding them. Okay, plus 3. So I got that. Is that a polynomial? Yeah, I got 1, 2, 3, 4. I think it's a quartic polynomial here. Not quartic. I don't know. It's monomial, monomial, binomial, trinomial, quartnomial. I don't know. There it is. Polynomial here. Okay, and of course this one here. If I multiply, right, am I going to have to go outside of my set to invent a new type of number to describe my answer here, or is a polynomial going to be sufficient for describing my answer? And it turns out if I multiply two polynomials together, I get a polynomial as an answer. So yeah, it is indeed a closed set under multiplication. Polynomials are a closed set under multiplication here, okay? Plus 7x. Okay, so what does it ask me to do? What do I have to answer here? So I do it all here. You'll always know, okay? So yes. Okay, yes. Polynomials are a closed set under multiplication. So hopefully in this problem, I've seen you guys multiply it all out. I just didn't do that for myself. I did that for you. I'm doing this for you to get practice on multiplying polynomials. Closed set under multiplication. Polynomials are closed set under multiplication. And then if you answer here, in other words, if you multiply two polynomials together, they're the same variable. You will also get a pair of polynomials as your answer. Yes. Give examples and explain how your answer is true for all one variable polynomials. Okay. You can say, well, all right, same logic here. We already knew that polynomials are closed, a closed set under addition, since multiplication is just repeated addition. It will be closed also. Okay, if it's true for addition, that law is going to be applied to multiplication because multiplication is just repeated addition, so it gets that property as well. Okay, thank you guys for watching. Hopefully, it's clear some things out with closure of sets, and we'll be dealing more with number sets in chapter in next semester when we talk about them more formally. What is an integer? We've talked about it a bit here. What's a whole number? What's a rational number? What's an irrational number? What's an imaginary number? Hey, these are all things that you should know about before Algebra 2. Thank you for watching. Take care, guys. I will see you soon, about a week or so away. Thank you for watching. That's it for your classwork. Just those two problems, then you got some homework tonight. Thank you. Turn in your homework to Google Classroom. Turn it in every day. Bye. Oh, looks at that handsome devil right there. Hi. Hello.